In this video, we're going to talk molecular orbital theory when you're using non-equivalent atoms, so heterodimers rather than homodimers, two different atoms. Let's take a look at NO. Nitric oxide was one of our examples of Lewis structures that don't quite work, where we have a free radical. And there's just nothing we can do about it. Lone pair, unpaired, double bond. Well, if we want to apply our MO theory to it, I've got nitrogen. It has its 2s and its 2p. And oxygen has its 2s and its 2p. And you'll notice, in terms of energy, they're lower. Well, oxygen has a greater Z effective. It's drawing in those electrons more. Its orbitals are at lower energy. And so we actually draw them physically lower. But this actually affects the bonds that we make. So when we have an MO, when they come to overlap, one of them is physically closer in energy to one atom than the other. When we make the antibonding, we're going to find that's the same deal. The sigma is closer to the original oxygen, and the sigma star is closer to the original nitrogen. What does that actually mean? Well, I have my nitrogen, I have my oxygen, and my s orbitals are going to overlap. Well, my nitrogen's orbital is a little bit bigger. My oxygen orbital is a little bit smaller. As they come together and they overlap, the density is physically closer to the nucleus from oxygen. When you try to draw this, what you'll find is that it's a little bit more over towards the oxygen. So if here's my center line, there's just more density on the oxygen side of it. The net result is that it is skewed a little bit out towards the oxygen side. So it looks a little bit more like the original oxygen atom. Not a lot, but enough that even though there is a net increase in the middle, it favors oxygen. Well, the antibonding orbital, because what's happening is that where they overlap is destructive, and it goes away, you destroy a lot more near the oxygen. And so it goes way out more this way. You've got your node. And there's not quite as much imbalance on the nitrogen. The net result is it looks a lot more like the nitrogen, and it looks a lot less like the oxygen. These are small perturbances at this point, but it means that our MO we create is different if we're bringing together different atoms. It's not perfectly symmetric the way our p orbitals were, or our s orbitals, when it was the same atom. All the shapes for our p orbitals interacting, all the shapes for s orbitals interacting, they were perfectly symmetric when it was the two atoms that were identical. Now this overall isn't a problem because the imbalance in the lower one is countered by the imbalance in the opposite direction in the top one. And so overall our two orbitals end up balancing out as a set, and so we maintain our symmetry. Well, this plays out in the p orbitals as well. And so as you make your sigma for your p orbital, you're going to overlap best closer to the oxygen. So the net effect is that when you make your shape, it's skewed towards the oxygen. Plus, minus, plus. And so if you kind of have your center line, it's more on the oxygen side. And it looks a little bit more like the p orbital from oxygen. It's still a mix of the two, but this general idea holds up for the rest of them. When you have non-equivalent atomic orbitals, the molecular orbital you make skews to look a little bit more like the nearer atomic orbital. As long as you have a series that is reasonably similar in energy, this is not a major effect. It skews things a little, but it won't affect properties too much. As we bring together our pi's and our anti-pi, and if we wanted one last pi star, we won't have enough electrons to fill it, but we can identify that it would be there. Well, nitrogen has 5 electrons, oxygen has 6, so we would start filling from the bottom. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. We would predict from this that NO should be paramagnetic and should have 1 unpaired electron. And that's actually what we see. Curious enough, it kind of matches our Lewis structure pretty well, and that's because Lewis structure is a reasonable idea most of the time. It can't always work, but it does its job fairly well. NO is indeed paramagnetic, and it has 1 unpaired electron. Let's look at HF. In this case, I've got my hydrogens 1s, and fluorine, well, remember as you go across the periodic table, your Z effective gets greater. So if we think about energy, and we have hydrogens 1s, and then we go to helium, well, it drops down. And then we go to lithium, the 1s has gone down, and the 2s is a little bit higher, which is why it takes a little bit less energy to ionize lithium than it does hydrogen. But these keep going down as you go to beryllium and boron and carbon and nitrogen. And oxygen and fluorine, they continue to decrease. The 2s does this as well. 2s goes down, 2s, and our 2p's show up. Well, the 2s keeps going down, and the 2p's go down, the 2p's go down, the 2p's go down, the 2p's go down. The actual result is that the 2p and the 2s for fluorine happen to be below the energy of the 1s of hydrogen. When I try to bring this together, I have the energy on the side and I have hydrogen with its 1s. Fluorine actually has its 2p's nearby and its 2s is way down. Fluorine has its 7 valence electrons. Hydrogen has its 1. Now you might try to pair the s's, as we've seen before, but they're actually so far out of whack energy-wise, their overlap is incredibly poor, to the point where it's basically nothing. They can't meaningfully overlap. If you try to create an orbital, they basically look exactly like fluorine, or exactly like hydrogen. That gives so little overlap that it isn't meaningful enough to hold a molecule together. But what does an s orbital do? Well, normally it just goes end on end with an s orbital. There's no reason it can't go end on end with a p orbital. It's just usually the p orbitals are out of energy range. The left and right p can line up with the s orbital, and they're more reasonably close to each other in energy. You'll get a shape that looks like this. Plus and minus, where they overlapped, might be a little bit bigger on this side. But where they overlapped in the middle, there's some constructive attraction. There's still a node centered on the fluorine, but there's definitely more density here in the middle than there was before the overlap. And our antibonding, so plus minus plus, they're going to destroy in the middle, and there's a node already in p orbital. You end up with a shape with two nodes. One of them is centered on the fluorine nucleus. So I have a plus and a minus, and one of them is centered on the overlap so that our hydrogen nucleus and our fluorine nucleus, well, here's a system with a double node. More nodes were higher in energy. And that's what we see. We've seen that with all the MOs. The lower energy ones had less nodes than the higher energy ones, at least for the same orbitals overlapping. In our case, though, these are sigmas. We have a sigma bonding and we have a sigma antibonding. Well, the other p orbitals, if I have my O and I have a p, plus, minus, and plus, and I overlap them, I get as much constructive here as destructive here. The up and down and in and out p orbital don't have any meaningful effect. So they don't do anything. There's no change in their energy. As I go to fill electrons, I had my 2s, it didn't change because nothing meaningful happened. So 2 of my 7 electrons go there. Well, there's 2, 3, 4, 5, 6, 7, and the 8th comes from the hydrogen. And so it looks like this. The MO for HF has what is just a fluorine 2s, a sigma overlap between an s and a p, 2 p orbitals that just look like fluorine, and an unused sigma antibonding. What we have to introduce here is non-bonding electrons. These are neither bonding nor antibonding because they're in orbitals that continue to look exactly like atomic orbitals. Not a little bit like, these look exactly like. There was no overlap, so they don't do anything. These are non-bonding. If I try to solve the bond order for HF, well, I have 2 bonding and no antibonding. So 2 minus 0 divided by 2 is 1. The molecular orbital theory shows that there should be a single bond, and that is what we see. And when we think about our Lewis structures, we think of a single bond, and that is what we see. So HF is an example where wildly different sets of orbitals interact. And the more divergent you get in energy, the less it's going to look like the standard filling pattern. But as a general rule, if you are elements in the upper right of the periodic table, you're going to follow our standard filling pattern. Sigma, sigma star for the S, sigma pi, pi star, sigma star for the P's.